Okay, good afternoon. Let's start lecture here, okay? So I have just a little bit left in the gear design, and then we'll finish that, and then we'll go on to the shaft design lectures, okay? Yeah. So in the previous two lectures, we have talked about the design of spur gear, helical gear, using AGMA equations. So the AGMA equations are basically a set of equations calculating bending and normal bending and contact stress, okay? And then also calculate the strength values, right, for bending stress and contact stress. So the formulas for for bending stress and contact stress are over here, and formulas for the strength value, okay, are given in these two equations. Okay, so you have the handouts for all the parameters in the previous lecture, right? Yeah. And at the end of the previous lecture, one thing I did is basically of course. So at the end of the previous lecture, what we did is we looked at the effect of all the AGMA equations. Let's see. Okay. So anyway, this will turn on shortly. Let's look at that two springs here. Okay. So this is basically what I'm saying here. We have used the AGMA equations, okay, in the previous lectures in terms of analysis and design, right? So, and in the previous lecture, then we also look at this by keeping a certain parameter, for example, the number of teeth unchanged, changing diametral pitch, then what's the effect, right? You can also look at if I change number of teeth but keeping the diametral pitch as constant, then what's the effect on the stress, right? So there's only one thing I want to touch upon is another scenario, because it's more of a to do with the design, okay, and here. Okay. So in this case here, let's just basically ask a question in here is how to choose the diametral pitch PD, okay, if material, okay, is selected. Okay. And this is very much related to the course design project. Okay. In the course design project, it's fairly open-ended. It only gives you options of material and only give you a range of the diametral pitch for you to pick, right? So the question is, which diametral pitch should you use? And why do you use that diametral pitch, right? This question here essentially, if you select the material, then how do I pick a diametral pitch? So for the gear design, you have given, I think, two different type of material. One is cast iron, the other is the steel. Okay. You could choose either cast iron or choose either the steel, no problem at all, right? Yeah. Let's say you decided to use one of the material. You can actually play out for both type materials. But if you pick a material already, so now comes the question of the value for the diametral pitch. So if you recall that in the previous lecture, we have the parameter which is this transmitted load WT. Transmitted WT is a function of the diametral pitch, because your pitch diameter right, depends on the diametric pitch. So this is another thing. You also have to determine the number of teeth, right? So you determine the number of teeth, and of course you don't know diametric pitch yet, right? Then you can decide on the pitch diameter. If we don't have a pitch diameter, then we won't be able to calculate this transmitted load WT, okay? Because WT times the half of the pitch diameter gives you the torque, right? Torque can be calculated. So torque based on the input power, and you can calculate the torque, okay, and the speed. And the other parameter that the dynamic effect factor kV is also a function of this pitch diameter d. So basically, it's a function of this diametric pitch here. Okay, the pitch line velocity v is also a diametric pitch function. So a lot of these parameters, Wt, the kV, kV basically is a part of the calculation, right, required for the kV. So it depends on the PD. Okay. Some other parameters like a size factor, like the rim diameter, you could basically keep them as a fixed. They are very small numbers. Sometimes you don't have to worry too much about these things here, right? Yeah. So bottom line is, if you look at the EGMA equation, right? In order to calculate the stress, I need to know Wt, I need to know the kV. Those are key parameters at here. So now, when you calculate the bending stress, okay, the bending stress depends on the diametric pitch, depends on the transmitted load, which is a function of PD, and also depends on the face width F, and that PD too, right? And then KO, KV, KO, KS, KM, KB, okay, and the rest of the parameters. So the rest of the parameters can be decided if you have a number of T's, and if you have some other information so given, you'll be able to know. But this one is question mark. This was a question mark here. This is a question mark here. This KV here is a question mark, right? And F at here is also a question mark for now, basically. Okay, yeah. So that's basically, we don't know what the face width yet, right? How we can pick the face width. Okay, yeah. So essentially, the bending stress at here is a function of a diametric pitch. PD is also a function of the face width, right? Function of face width. Okay. Okay, so let's leave this one temporarily as it is. You know, we know how to calculate the stress, but we have to decide on the value PD and F first in order to calculate the sigma B. Okay. But what we do know is in this part of the question here is you are given the material, or you choose the material already, right? You're given or choose the material. So once you have the material, if you look at AGMA equation, so when you have the material, then you would be able to have what? The ST and SC value. Okay, so that's your stress numbers, right? So the stress numbers will be given. And also, if you have the number of cycles, you'll be able to find the YN, KT, KR. So basically, you'll be able to find from these equations the so-called allowable stress here. If you don't really care about the safety factor is 1. So what you're going to get is essentially the maximum allowable stress, right? Maximum allowable value. Okay. Okay. So this is good. So given material, we can have. Okay. What we can have, for example, we can have our maximum allowable. Okay. Sigma B, which is YN over let's say you have a safety factor SF, and then KT, KR, and ST. So you could calculate this one based on the given materials, right? Given materials here. Okay. So now all we can do is we can substitute, temporarily substitute this value over here, over to the left side of this equation. Right? So that equation is for calculating the actual bending stress, but we can't calculate yet, right? So if we give a material, what we can do, we can substitute the maximum value over here, right? Maximum value over here. Now, if I substitute the maximum value over here, then I can move the F to the left side and move the maximum value to this denominator right here. So that equation, I can rewrite it as F equal to PD WT PD, and then this bottom here is a sigma, the maximum allowable. Okay, maximum allowable here, and then KV over here. Okay, KO, KS, KM, the rest of the stuff. Okay. So then we can reshuffle it a little bit to get a new expression for the phase width F. Okay, for the phase width F at here. So why we're trying to do this is you look at the new expression at here. So basically the phase width F, okay, and looking at the whole right side here, it's a function of what? The diametral pitch. Okay, it's a function of diametral pitch. At the same time, there is a empirical equation, if you recall, that we given for phase width, and that's 8 over PD and 16 over PD. Okay, yeah. So basically, this empirical equation is actually two functions. One is F equal to 8 over PD, and the other is 16 over PD here, right? So they're like two boundaries basically, right? Two curves serving as two boundaries. And then you have the third equation. So there's 1, 2, 3. So we have three equations that are here, trying to guide us to find a suitable value for the phase width F. That makes sense, right? So the next thing what you can do now is, okay, you can create, okay, a table. So you can create a table right here. Okay. So here, here is a PD number. Then you can choose 2 and 4, right? Something like this, and you keep going. PD numbers here. Then you can you have your function. Let's call this is function F1. This is F2. This is function F3, for example. So you can have you can generate basically what is F1 value, F2 value, what's F3 value, right? Based on the three expressions. So if you substitute a different PD into this expression, right, you will be able to find a certain values based on equation 1, 2, 3. Okay? Yeah. And then from here you can plot a diagram, right? You can plot curves out here, like basically this is the tutorial what you see in the previous 2 weeks of the tutorial here. Okay? So now you can plot it out, which is this. Okay, so you'll be able to plot 3 curves. One curve, this red one here, is this one here. Okay, is this. And then this green and the purple one are the 2 curves corresponding to equation 1 and 2. Okay. So this way you can have 3 curves, right? All of them are related to finding an appropriate value for the phase width. But what we want is a one phase width value that satisfies all the 3 equations. So you look at the curves that are here. There are only theoretically only one dot satisfy these 3 equations, right? And that one dot corresponding to a certain diametral pitch, which is a 10 at here. Okay, yeah. So that's somehow you can start your calculation for the diametral pitch PD, right? So from here, you can start. Okay, so I think I recommend PD equal to 10, for example. Okay, based on these 3 curves at here. Is that good? So that's one way to start you off with finding a diametral pitch. Now, this is not necessarily absolute constraint sometimes. So if you look at the curve, the 8 and the 12, okay, are just barely outside the boundary here. So you could also choose 8 or 12 just to basically start your iterations, right? Yeah. If a 10 doesn't work, you can choose 8, right? Yeah. So that's basically the approach right here is to give you a suggested starting value for the diametral pitch, okay, and alternatively coming up a value for the face width. Okay, so that's one thing that you can use when you design for the gear, right? Any questions on this part? Is all good? Okay. Yeah. Okay, so that's basically all about the gear. Okay, and now let's look at the shaft design here. Okay, let's look at shaft design. I'm gonna go over using my PowerPoint some basically considerations that's associated with the shaft design. Okay, and then once we finish all this consideration, then we can go through an example. Okay, to look at an actual shaft design question. Okay. Okay. For this part of learning objective, essentially we wanted to study basically the key functions of a shaft in mechanical design. What does shaft do, right? What can we use a shaft as a what type of function can we use a shaft for? And we want to learn how to create the free body diagram for the shaft, of course. I actually learned quite a bit. And we want to use them to determine the stress, okay, at the key locations, basically at the critical locations. Okay, and then we're supposed to be able to design to come with a minimum shaft diameter. Okay. So that's the ultimate purpose of it here. This diagram, and I think I have shown you this diagram number of times. Okay, so for now we're at this location, basically rotational to rotational power transformation. It's part of the gear, shaft, and the case and the bearings, right? Yeah. So what is a function of a shaft? Okay, shaft is a rotating mechanical structure. Okay, for transmitting power and motion. Okay. Exceptions, in the old times, there's also non-rotating shaft, okay, like in the horse and the buggy sense. Okay. And you also use a shaft to carry a wide range of mechanical elements. So I'll show you in a couple pictures next, basically, what type of elements typically a shaft can carry, right? The other part of the function of shaft is it's a structure that supports load. You use a shaft to carry a gear or to carry a pulley, so there inevitably will be a torque or force, okay, acting on the shaft. So the shaft needs to be designed to withstand those loads, okay, from perspective of deflection and strains. Okay, so here's a number of a couple of examples that are here. Okay, so in this diagram here, it shows you basically a so-called planar arbor. Essentially, there's a cutting tool at here. Okay, it's a fairly big cut heavy and cutting tools at here. Okay, if you remove the cutting tool, and the shaft will be exposed. Okay, like this. Right, it is supported by a bearing over there. Okay. So the question, when you look at this kind of actual diagram, actual system in here, then the question is, what type of stress, okay, would be important to analyze for the shafts at here? Right. So in other words, what type of stress do you think exists in this simple system at here? Right? What type of stress? Bending? Yeah. What else? Torque will result in torsional stress. Yes. Is there anything else you think is critical? Shear. What type of shear? Torsional shear. There's another shear, type of shear that could be possible. As I should mention, because the cutting tool is very heavy, right? If you look at that, the mounting the cutting tools here. So at this location here, what could be the possible type of stress due to the weight of the cutting tool? What do we call that? The damage? Direct shear, right? Yeah. So that's basically the type of stress that could be existing at this shaft here, right? Yeah. Another thing that will come back later, essentially, because it's a fatigue loading, and essentially we're going to have to be able to identify what type of fatigue loading. Fluctuating. If it's fluctuating type of loading, what's the amplitude? What's the mean value, right? Whether if there is a mean value or whether there is an amplitude. So that's all up to the actual loading condition. And this one is a similar. It's a very similar. It's not a same system, but the type of stress are quite similar to the other picture here. So the shaft basically carries, a pulley at here, okay, and the power is transmitted somewhere else. Okay. So the same question: what type of stress would be important to analyze for the shaft? This portion of the shaft at here, right? So if you think about the pulley, there will be a force, right, on either side of the pulley. So there will be a force acting on the shaft, and there will be a torque, right? So all of these two, at least these two, will generate bending normal stress, and at least will generate the torsional stress. Okay, and also very similar to the other picture here. So you have a force set here, and then this is a very short shaft here. So at the end of the shaft, there is quite possibly you have to be careful with the direct shear type of stress, right? So that's the this type here. So we call that combination, or it's a combined bending normal, torsional shear, and direct shear. Okay. So this is basically a list of the elements that the shaft, typical elements the shaft can carry or can be mounted to the shaft, right? So if we were transferring power, then we can have wheels or brakes or fans or cranks, okay? Or gears or pulleys. And supporting the shaft, we can carry, we need the bearing on the shaft. To support the load, okay, we need the pulley, or we need some maybe leaf springs. Store energy, we can use a flywheel. For some type of actuation, we can use a cam. And for better, basically protection of the environment, so we can use the seals. So these are basically the typical type of elements a shaft can carry, right? And the next point is, how can we locate this element, okay, exactly or precisely at a certain location, okay? So that's called the locating elements, right? For example, you want your gear to be exactly at this location, okay? Or you want this gear at exactly this location, right? So how do we do that? So there are a number of ways of doing it by using basically a different type of the so-called locating elements. One of the most used ones here is the so-called shaft shoulder. So here is the shoulder. So you look at this is basically flat, and then there's a shoulder up and a shoulder down. Okay, that's the shoulder. So we use the shoulder to precisely locate the gears at this location. Okay, so that the next question basically is when you design for the shaft, stepped shaft, right, is the desired basically structure, okay, or layout that you should have for the course project. But just a shoulder is not enough to locate this element, right? So, for example, you put the shaft against the shoulder over here now, but then we also need to prevent the shaft to move axially, right? You can't let it all the way wobble through this, falling off the shaft. So we can use this thing here, which is called a sleeve or spacer, to put a spacer between the bearing and the shaft, to basically prevent the shaft from going axial direction. Okay. And you have the bearing at it here. In order to prevent the bearing from moving away, so you can use this little symbol here that's basically referring to the snap ring at it here. So you have a snap ring right outside the bearing to prevent it from moving away from the shaft, right? Yeah. In this case, there's I guess this one didn't have anything else, but you could also use nut and washer, cotter and washer, or set screw to basically trying to fix some of the elements on the shaft. So, for example, you have a shaft, you have a gear here, and the gear has a hub. So instead of using a sleeve at here to fix the gear on the shaft, you could also use a set screw all the way through the shaft, then fix it to the shaft, right? Through the gears to the shaft. Okay, so that's another way, basically fixing it to look axially. So the next picture is a little bit more example here. So this one, you see here, in order to fix this hub, you use a clamp and collar type of. This is very rigid, okay, for essentially very high speed motion. Okay. And this one here, using the K, so it's basically this is called a Woodruff K. We're going to learn that. Using the Woodruff K here to transmit the power from shaft to the Woodruff K and then to the gear. Okay, so that's basically it's a coupling. Okay, and then at the end here it's carrying a sheave. So this one, the sheave is fixed using a cotter or tapered pin, right, to go through this shaft and fix it on the shaft. Okay, and this one also had example using a snap ring as the other example. Okay. So those are basically examples of how you can fix your shaft to the fix your elements to the shaft, right? So when you design for your system, you need to bear that in mind. Okay, so we're not constructing an actual system, but when you design your actual system, you need to have a reasonable, basically, mechanism to locate the element and also to fix the element at a certain location. Okay. So some of the guidelines here, some of the guidelines in terms of the design for the shaft. This one here, the guideline basically takes this bending moment into consideration. One of the basic facts about bending moment is when you have longer shaft, right? Even though you have the same loading force, then there will be higher bending moment, right, for longer shaft compared to a shorter shaft. Okay, so that's a basic fact. Bending moment will generate the bending normal stress, so you want to minimize the bending moment, and that basically means what? You want to have a shorter shaft as possible, as much possible. Of course, sometimes it's not that possible, but you do need the shaft to carry elements, right? So you do need a certain minimum lengths in order to do that. But bear in mind, don't design an excessive shaft, right, to prevent the unnecessary bending moment and possibly also unnecessary deflection. Okay. Yeah. Bending moment is higher bending moment is not good, and if it's even worse, if you superimpose the bending moment with what? With the stress concentration, right? So this is why another guideline here is you want to minimize the stress concentration effect is to move the maximum bending moment location away from the stress concentration location. Okay, so where do you see stress concentration? You probably see stress concentration at like this one here, at the shaft shoulder at the fillet location. Okay, that's one very common location. At the K6 location, right? And some other shoulder location, right? Yeah. At the snap ring location. So whenever you have a groove. So what you do want is you don't want your bending moment to be particularly high at that location, essentially. Okay? Yeah. So just bear that in mind when you design your system. Okay. Back to the shaft layout, right? We said it's best the shaft, okay, to be designed as a stepped, basically layout. Okay. The typical process, okay, is before you start analyzing a shaft, or before you even start calculating the minimum value for the shaft diameter, you need to determine the layout of the shaft first, which is part of the assignment's question for the next one. Okay. You have to basically think about the layout. What the layout basically means is, okay, so draw the steps out. You want to put, let's say, a bearing over here, or a gear over here, or something else over here, right? So that has to be planned out initially, okay? And then you can perform free body diagram, okay, obtain shear moment diagram. So planning out doesn't necessarily just means you plan out the layout. You actually also need to think about the lengths. You would have to say, okay, for my project, I need this portion to be this much length and this portion to be this much length, right? So that has to be determined too. If you find this is not very reasonable or not very practical, you have to change. So you actually have to recalculate everything, right? Once your length is changed, okay? So that's important. Have a reasonable layout plus a reasonable shaft length, okay, for different sections of the shaft. It's important to reduce yourself a lot of potential calculations. As we said, the geometry of the shaft generally that of stepped cylinder, and the use of the shaft shoulder is an excellent mean of actually locating the shaft element, okay, and carry any thrust loads. Okay, yeah. A shoulder also provides a solid support to minimize deflection and vibrations. If you have a low magnitude force, you can also use the shoulder to construct it with the retaining rings in groove or clamp-on collars, right, to fix the element at a location. And a few more here. So in general, it is best to support load-carrying components between bearings rather than cantilever the outboard of the bearing. So basically, if you have a gear, then it's probably best to sit it in between the bearing. Okay, but not necessarily is always the case. Some elements that has to be basically carried, like in the cantilever type of a sense. So like the sprocket or sheave, right? You have a basically a bell, okay, driving the sheave. So that has to be outside the bearing, right? So that just bear in mind. In our case, when you design a gearbox, your gear will be between the two bearings. Okay. Pulleys and sprockets often needed to be mounted outboard, okay, for ease of installation. The length of the cantilever should be kept short to minimize deflection. Okay. Another important thing is you should always try to use only two bearings to carry all of these elements. Okay, it's because if you use more bearings, then whenever you use more than two bearings, then there will be inevitably there's this alignment issue coming to the picture, right? If they're not aligned properly, then the middle bearing or the other bearing can be damaged quite easily. Okay. All right. So here's an example here. Okay. So let's say the customer giving you a certain task is I have two gears at here. Okay. So one small gear, one bigger gear. Both are helical gear, right? As you can see. And I want you to design a shaft. Right. There are two bearings over here. So design a shaft to carry these elements. Okay? Yeah. So there are different ways of designing. As you can see, one of the solution at here is to come up with a stepped shoulder structure layout to carry the two gears and also locate them through using the shoulder. Okay. The same thing for the bearings at here. Okay. Between this gear and the bearing, there's also using a sleeve at here, basically to prevent it from moving away or axially. And for the small gear here, or which is a pinion possibly. Okay. So for the small one in here, one of the very common solution is you build the small pinion or the gear as an integral part of the shaft. So basically, you manufacture the shaft and the gear as one whole piece. Okay, as one whole piece, which is also very doable, right? Especially if this is a small one here. Okay, and that's actually quite a bit of advantage. So your gear here is basically integral part of the shaft. So there's reducing a lot of potential problems, right? Yeah. So that's one possible solution here. Okay. Yeah. Because when you have a small gear, typically you have a small space set here. How you can locate that? Because you probably cannot have a hub at here for the gear, right? Then you won't be able to use a set screw for that. So that's one of the reasons why you can consider to build it integral part as your gear. You can choose the same thing for your course project too. Okay. Yeah. Okay, so continue. In case axle load is not trivial, so if you have a helical gear or bevel gear, so there's inevitably there will be axial load. Axial load is a load along the shaft direction. Okay, so radial load or horizontal load, that's just direction perpendicular to the shaft, right? So if axial load is inevitable, right, or non-trivial, then you have to come up with the ways to transmit the axial load, okay, from the element to the shaft, and then from the shaft to the bearing, and from the bearing to the housing, from the housing to the ground. Okay, so you have to let the force flow through all the elements to the ground, basically. Okay, yeah. And you also have to also make sure that typically we only need one bearing to carry the axial load, and then the other bearing you make it with so-called non-locating or so-called floating. So basically, that gives you certain freedom, okay, to accommodate the length change of the shaft due to thermal or other type of reasons. So you see, show you a picture here. It's taken from the textbook. Okay, there is a small bevel gear here driving the big one. Okay, so the for the big shaft at here, right? So for the mini bevel gear, basically there will be axial load along this shaft at here. So as you can see, you have basically a thrust bearing at here to take care of that thrust load. So the thrust load will go to the shoulder, from the shoulder to the bearing, then the bearing goes to housing, and the housing is probably connected to the ground, finally go to the earth, right? Yeah. And this side of the bearing, you look at it, that's so-called rigidly fixed. So you see the bearing here, one side is against the shoulder, the other side there's this covered here, rigidly pressed against the bearing. So this bearing is rigidly fixed at here. But the other side of the bearing, look at that thrust bearing here, right? That bearing is actually what we call the floating. So the shaft here can expand, okay, to a certain degree, okay, because of the floating mechanism structure at here, right? So that gives you an example, basically, how you can design your bearing to accommodate that type of consideration. Okay, yeah. Whenever you have a shaft, whenever you have a step shoulder, and it's inevitable that you will have stress concentration. Okay, yeah. So to relieve the stress concentration, the pictures that are here shows you a couple of ways how you can relieve stress concentration. The first one here has a undercut at the shoulder, Okay, so we call it basically a large radius undercut. And this one here has a shoulder relief groove. So this is basically the shoulder relief groove here. And this one has the so-called large radius relief groove. So there's a relief groove around the shaft. Okay. All of this will provide certain means to reduce the stress value. The flow of the stress is shown right here. So, but either way, especially like when you design for the shaft, even if you don't have this one here, you probably will have a fillet at the location. So either way, okay, later we'll show you. You will have to consider the stress concentration, and especially this particular, it's a fatigue stress concentration. Okay, yeah. So you're gonna have to take that in consideration when you design for the shaft, design for the minimum shaft diameter. Okay. Any questions so far? Yeah. Okay. So another reason or effect that you had to consider when you design for the shaft is shaft. You need to use bearing to support the shaft. So the information on the bearing, and often in time, will dictate the shaft diameter. Okay. So here's an example here. Okay. This figure is not that big, but this table right here, okay, this table is taken from part of the basically bearing catalog. So if I look at this bearing catalog here, the first column give you the ball size of the bearing. So 10 millimeter, 12, 20. So those are basically the so-called ball size of the bearing here, right? Okay. And then also, of course, the outer diameter, the width of the bearing. Okay. And then there are a couple more information here, basically called the shoulder. So if you look at this column here, right? They are, what do they call it? DS, DH, and here. So this is DS, this is DH. And there's an illustration at here showing what DS is, what DH is. So DS is this parameter. DH is this parameter. Okay? Yeah. And then there's also one more parameter, which is the capital D, and that refers to the, really hard to read. That's the shaft diameter, right? That's the shaft diameter right here, the capital D. Okay, yeah. So what this basically means is this. You see that DS value, right? The DS value is basically, it's what? It's the shaft diameter on the next level of the step, isn't it, right? This DS right here, okay, is basically this capital D value here. Okay, it's basically the capital D. Okay? And the small d right here is basically what? What value is it? The small d. The small d here is basically from the catalog. That's the bearing ball size, right? Bearing ball size. Okay? Yeah. Now, if you look at the ratio between the DS and the D, so basically the ratio right here, okay, it's always somewhere between 1.2 and 1.5. So basically what it means is it's recommended that the step ratio, right, is between 1.2 and 1.5. Okay. And this is essentially dictated by the bearing catalog at here. You can change. If you basically means if you pick a bearing, right, then you have to use these numbers here, these dimensions that are here, okay, in order for you to carry that bearing. Does that make sense? Right? So the bearing catalog here, so you can calculate minimum value. So I'll show you when we do an example, we'll see that. You can calculate minimum value. You calculate, let's say, the small d you calculate, say, to be, I don't know, maybe 8 millimeter, for example. Okay, you calculate to be 8 millimeter. Then you come back here, you're going to have to pick a bearing. When you pick a bearing, then based on the minimum value 8, then of course it's the 10 will be enough, right? So you will pick a bearing that is 10 millimeter. So when you pick a bearing that's 10 millimeter, basically means what? Your original shaft calculated 8, you're going to have to bump it to actual 10 millimeter. Okay? Yeah. So if you pick this bearing, then your next step here, the capital D, will be this value, 12.5. So that's basically the bearing catalog will give you a lot of useful information when you decide, when you have a final make a final decision on the shaft size. Okay, so bear that in mind. It's not, the minimum value is not enough. Okay, you're gonna have to make a decision based on several things together. Okay, to come up with the final shaft size. Right. And this ratio 1.2 to 1.5 is also a design recommendation that we can use when we design our layouts or the size for the shaft. Okay. Yeah. In the bearing catalog, there's also one more parameter given is this. So you're going to put the bearing against the shoulder of the shaft. So the bearing, the housing, there is a corner here. There's a basically called the corner radius. Okay. So the bearing metal shaft, metal housing has a radius here, and there's also a fillet radius at the shoulder location for the shaft, right? So there are two radius. One is the bearing radius, the corner radius. There's another radius which is the shaft fillet radius, right? Yeah. Now, the bearing's corner radius, you can find it from not here, but there should be. In a more detailed catalog, you should have it. So this RA, you can find it in the bearing catalog, right? When you design for the shaft, then you have to be very careful. Your fillet radius needs to be what? The fillet radius for the shaft needs to be bigger or smaller than the corner radius? Smaller, right? So that's something that you have to be very careful. And this kind of detail, you know, I may not be able to identify, but because there's too many things to read. So, but you have to be very careful in the actual design. That's something that type of detail you have to basically pay attention to, right? Okay. Yeah. Okay. So that's from bearing catalog. You know what type of information you can make use of, right? Okay, and a few more on the shaft considerations at here. Okay, a few more slides at here. First of all, you know, the location of the case, okay, should be along the same reference. So this is representing there's a key at here, there's a key at here. So these two slots, okay, these two slots should be along the same reference line. You don't want one slot here, like 90 degrees or 180 degrees apart from each other, okay? And because if that's the case, then you can cause some kind of excessive twist about the shaft, okay? It's recommended to use a chamfer at the output end of the shaft to facilitate assembly. Okay, so this is the chamfer means that here, right? You're going to mount the bearing, so it's easier to have a chamfer over here. In order to fix the gear against the shoulder, so this is the shoulder, here's the gear. It is recommended you basically have a slightly protrusion, which is let's say 2 to 3 millimeters longer than the shoulder location. So then your spacer or sleeve can precisely or basically confidently fix that gear at the location, right? Yeah. If you design to be flush, you know, probably due to manufacturing error or due to some other reasons, so that if that edge is actually slightly shorter than this shoulder here, no, they're not really in contact, right? Yeah. So that's the reason. we also want to improve the loading condition. Okay, so this diagram here gives you a perfect example of how you can improve the loading condition. The first diagram shows that you have an input gear over here, and then 3 output gears on this side here. Okay, so you have an input torque here, and then you have 3 output gears here. If you draw a torque diagram, okay, if you draw a torque diagram, basically you cut a cross section over here. You see the T1. You cut a cross section here because this is basically T2. So you have a T1 minus T2. You end up over here. Cut a cross section, end up here, cross section. So that's basically the torque diagram based on this structure layout, right? Yeah. And then your maximum torque, your torque is T1. That makes sense, right? So that at that location in the shaft, you have this much of a torque T1 over here. Okay? But if you change the layout slightly, see that? If you change the input and put it in between these 2 output here, okay? Your input is still T1. Okay? Your input is still T1. And the output here, for this output here, which is this output, still T2. So now if you cut a cross section over here, right, over here, so you can see now the torque diagram is quite different now, right? It's quite different. And then the maximum torque along the shaft here, it's not the T1 anymore. This is what? It's a T1 minus T2, right? So that's your maximum here. Okay. So that reduces basically the possible stress on the shaft here, right? So the arrangement of the elements along the shaft will actually play a different effect on the distribution of the stress here. So just bear in mind of this different type of arrangements, right? Yeah. Okay, so now I talk a lot of things already. Okay, so I'm going to give you an example here. Okay, this is the yield design example. So there are a lot of actually problems in this example here. So I want you to point out some of the mistakes, okay, in this example, okay, based on what we just learned. In this example, what happens is basically you have a gear here, you have a shaft, right, and this white one here is the housing. And you have a bearing over here and here, and this is the spacer over here, okay? And this is some housing again. This is the case at here. This is the K. Okay. The case basically will carry another element. Okay. This element, I don't know what it is, but it will be basically driving something else. Okay. Okay. So and there's a cover over here. So looking at this one here, can you identify, yes, Radis, can you identify certain problems?
The keys here, because we have a key for the big here, and we have a key on the far right.
Very good. So these two are not in the same reference line, right? Yes, that's one mistake. Anything else?
Spacers, a lot of spacers with the shaft here.
This spacer, you mean? Yeah. This spacer, the size-wise seems okay. The not okay is actually it's the height. So why is the height not okay? You see where did it go now? The height goes all the way to here now, right? So that, and this is the bearing, right? This is the bearing at here. So that bearing, possibly here there is a seal. So that spacer, instead of just in contact with the housing of the bearing, it's very possibly going to be in contact with the cover or the seal of the bearing over here. So that's not what you really want. So that's the height at here needs to be reduced to somewhere over here. Okay? Yeah. Any other problems in this design example here? And this is a cover, right? This is a cover here. Okay, so the cover covering the housing in here. Okay, yeah. Anybody else can point out certain mistakes? Remember, the end of the shaft we recommend to be what? The shaft at the end, the edge right here needs to be chamfered, right? Yeah. So that edge over here, okay, you want it to be chamfered there, okay? Yeah. And if I see the height of this, the sleeve is too high, needs to be reduced. Look at this shoulder. Look at the shaft shoulder here. What do you think of the shaft shoulder over here? It's the same problem in this, right? So the shaft shoulder should also needs to be reduced. Okay, so this one needs to be reduced to somewhere over here. Okay, somewhere over here. And then the other thing is, you see this is the cover, right? This is the cover, and it'll be metal, of course. Okay, so the cover right now is in touch with the shaft. You think about it, the shaft will rotate, and then this cover is metal and it's fixed. So you have a rotating element in contact with a fixed element. That's not good, right? That's not good. The cover is supposed to be a protection. It's more of a protecting foreign elements going into this the gearbox. So what you need is basically over at the contact location here, you need a ring which is serving as a seal. It's a plastic seal, or it's not a metal contact over there. Okay, so this is the sort of the summary of the mistakes that we just pointed out over here, right? A number of things. There's a seal, things. Okay, and a couple things more here is between the housing and the cover here, maybe another seal, and also this location, right? Yeah. So this is reduced, and that gear here, see that length is slightly elongated, okay, to reflect the requirements, right? Not instead of flush. And also over here, we didn't use a step shoulder here, so the new design used a step shoulder to locate this element precisely at this location. Okay. Yeah. Now this shoulder, I'm not sure this is necessary, but this shoulder is definitely necessary, and there's a chamfer right here. Okay. Yeah. So that's the type. Yes.
In this configuration, should there be any room beside one of the bearings to account for any non-masonry?
It should. Yeah. This is what we call a very rigid type of basically locating. Yeah. So what I'm saying is not that it's not okay, right? So for some scenario, if you wanted to have a very rigid, very stiff type of locating, so you can have on both ends to be basically both locating type of a bearing, okay, instead of floating one end, right? Yeah. So basically, you think there's very minimum expansion because of temperature, right? Yeah. But otherwise, you should design one side to be actually floating. Okay. Yeah. So this one here, as a matter of fact, there is a little bit floating in here. If you look at the bottom here, it's not very much, but it can move slightly to that direction along the shaft a little bit. Okay. Yeah. Okay. So these are about basically design considerations for shaft. Okay. There are a few more things that's very specific now. Basically, it's about the stress concentration. Okay. Yeah. Design is very much different from analysis, because when you do analysis, you were given the size, the length, and the fillet radius, the loading, right? And you can go ahead and then find the stress concentration factor, find all the values specifically, precisely, right? That's design. That's analysis. Okay. But for design, initially, right? Let's say the shaft, the shaft size is D or capital D. You don't know, right? Well, how do I know whether it's 2 inch or 3 inch or 1.5? Who knows, right? We don't know. Okay. So we had to calculate certain minimum value first. And if we don't know the capital D's or small d's, okay, then we will not be able to find the stress concentration factor. And the stress concentration factor is part of the parameter that you need to basically to calculate the safety factor, essentially, right? So there's a couple of things. The things are coupled here, right? Then how do we do that then, right? You know, if you want to calculate the minimum shaft diameter, which I will show you a formula, right, in the handout that you also have it. So you can calculate this minimum shaft diameter, but you do need this the stress concentration factor right here. So what we do now is you have to start somewhere, right? You got to start somewhere. That somewhere basically is an estimated or conservative value that you should use from the beginning. Not the final value it's going to be, but it's some value that you have to start with. So this is basically what we call the conservative values we can use to for the stress concentration. For example, if you look at this diagram, this is basically a loading condition for a fillet under bending moment. If you look at the diagram here, given ratio between this R and a D 0.02, and that's a typical ratio that you probably use for shaft design. The maximum stress concentration factor for a capital D over small d 1.5, and that 1.5 are based on the catalog, the bearings. Remember the bearing, right? When you calculate the ratio between two adjacent shaft step shoulders is between 1.2 and 1.5. And if you use this combination, you'll find 2.7 is roughly the maximum value for the KT. And if you look at this one on a torsion, with the similar set here, the KTS is about 2.2 here, is about the maximum here. So maximum basically means that's the most conservative, right? And even though I don't know the shaft size or R value, I can start the calculation by using this maximum 2.2, 2.7. And if I use that, things shouldn't go wrong, right? Because that's conservative value. And that's basically some of the value. You can even use it higher than that. One example we're going to show that. We use an even higher value than this 2.2, 2.7. So using conservative value to start your calculation, right? Start the first round of calculation is important. Okay, it's where you can get started here. Similarly for a K-sit, if you have a K-sit here, okay, here's the radius of the K-sit here. This is called basically the groove type of K-sit. And then if you use this ratio here, you'll find KT is about 2.2, KTS is about 3. Okay, so that's basically what you find from this figure. Now in this figure, it's actually we don't have it in our textbook, and I grabbed it from another textbook. So you can take a look at this PowerPoint if you wanted to use this figure here. Okay. Over here, okay, it shows you two different type of K-sit. One is basically a sledge runner, and the other is a profiled. The tool basically uses two different type of tools to machine out this K-sit. Okay. In our case, we typically will use this profiled type of K-sit at here. Okay. Yeah. As a matter of fact, the textbook table 7.1 give you 2.2, 2.7, okay, for the shoulder, and for the end mill K-sit, it's 2.143. So that's very much similar value to the values given from this figure at here. Okay, so that's the conservative value you should use. Basically, table 7.1, this row and this row at here is your starting point value for your KT and KTS. Okay, one for the shoulder fillet, one for the K-sit, Okay, yeah, we're going to look at an example how we can make use of this one here. Another important information is make sure that your K6 should be at least a distance of d/10 from the start of the shoulder fillets. Okay. Essentially, basically means if this is the K6 location, if the next location is the shoulder, then make sure this one is not too close to the shoulder fillet, right? Because the fillet location is stress concentration. K6 is the stress concentration. If put these things together, you got a super stress concentration there. Basically, that's not good, right? So make sure this K6, and I've seen that previously. If you design a K6, don't make it too close to the fillet, basically. All right? Yeah. So, and now that this is basically up to here, it's all about a general concept or guidelines in terms of the shaft design. Okay. When design, we do need the formula, right? So the next few slides give you the formula, which is the formulas in the handouts there. Okay. As a matter of fact, the formulas given at here are nothing new. We actually already designed or derived from previous lectures here. Okay. Yeah. So I'll show you a couple of things. So the formula at here. Okay. In this diagram here, basically, it includes the possible type of force that a shaft can experience. You can have axial force, shear force, or bending force, or torsional force, right? So any type of force could be a possibility. Torque give you the torsion, bending moment give you this. If you carry a very heavy element, you can have a shear force. If you have a helical gear or bevel gear, there will be axial force along the shaft, right? So those are the possibilities. Okay, and each one of the force, think about it, right? Each one of the force can be constant force, or they can be fluctuating force, right? So depends on the loading condition, of course. Okay, you can put them together, you know, but the question is, how do we put them together? That's what we call the combined loading condition, right? Combining different type of loadings together, combined loading condition. Well, when you have a combined loading condition, in the previous lecture, what do we use? We use basically one Mesi's equation to calculate the equivalent to sigma A prime and sigma M prime. Okay, so that's the some of the equations here, and I'll show you. But this diagram, this slide here, what it give you is where would be a critical location. Critical location meaning locations at the fillet location, okay, like a shoulder or K6, okay, or if you have a snap rings or splines, okay. So those are snap rings. Probably there's one over there. So those are possibly fillet critical locations. Okay, so basically anywhere with a change of geometry that is not uniform geometry, then it could be very well that should be a point of interest for you to analyze. Okay. You need to select the feeder criteria, modify Guttman, Gerber line, doesn't matter which one you choose. Okay, and we need to determine the material property that can be looked up, no problem at all. And we have to determine stress concentration factor. So this one here, you can't, most of the time you cannot decide right away. So if you can't decide right away, then you have to basically come up with the conservative values, like what we did in a few slides before, to start your calculation. Okay, and then we have to determine safety factor at the end. Safety factor you already given, so you probably require to design for, let's say, safety factor equal to 2, for example. With this, you can try to find a minimum shaft diameter using the feeder criteria. Okay, yeah. This diagram, these numbers here shows you a suggested safety factor under different type of loading condition or for different type of materials. Okay. Those are the feeder criteria that we have used previously, right? Yeah, you have a sigma A, sigma M, but this is for simple loading. But in our case, we have combined loading. So we need to calculate sigma A prime and sigma M prime using the von Mises formula. So here's one example here, right? Here's one example. If you have, let's say for example, let me probably see here. So let's see if I have a shaft like this, okay? Not working. Okay, so let's say I have a shaft like this, okay? If you have a force, okay, supported by bearings at here, and then you have a certain torque, okay, applied to the shaft, okay, and the shaft itself is rotating at omega at here, okay? So you have a T at here, right? And this is a very typical scenario when you design for a shaft, right? Maybe you know, you have basically a gear at this location, and then there's a pinion on the top, right? So the pinion drives the gear, and then the outputs of the shaft, let's say this is outputs at here, right? Okay. So if you look at this kind of a structure at here, and if you're going to design for the shaft, so first step, you have to basically identify as what type of stress exists in the shaft, right? So if the shaft is rotating and F is constant, T is, both these are constant, okay? So basically you have the forces and the torque are stationary, they're not going to change, okay? But the shaft is rotating, right? The shaft is rotating here. So basically what it means now is the F will generate bending moment, right? Will generate bending moment. Now because that the shaft rotating, F is constant, so what you actually generate here is MA is not 0 and MM is 0. So you get a basically bending moment amplitude not 0, but bending moment mean value is 0. And then the T at here is a constant one. And then the shaft is rotating, so that really doesn't matter. So the T at here will generate the TA is equal to 0 and TM not to 0. That makes sense, right? So if this is the only two type of forces, let's say if this is spur gear, right? If this is spur gear, and that's it, you basically you don't have axial load. If this is helical gear, then you would have axial load maybe in one direction, right? Yeah. But anyway, so let's say if this is spur gear designing here, and that's the type of a the type of a loading you have. Then MA yield sigma A, and MM no sigma M, and TM yield tau M over here, right? Yield tau M. Okay. Yeah. And that's how you would use basically to calculate your sigma A prime and tau. So basically how you calculate sigma A prime and the sigma M prime. Okay. So you can calculate sigma A prime and sigma M prime. And sigma A prime and sigma M prime are the values that you will enter into the design equation here, which is what I show you over here in terms of the design here, right? So you see here, this one actually a little more general. It assumes that both has MA, MM and TA, TM. Then you calculate sigma A and sigma A prime and sigma M prime using the von Mises stress component. Once you finish the calculation, you plug it into the design equation. In this case here, they use the Gerber design equation. Plug it into here, you get final equation, which is this. The A and B value are listed over here. then we can solve the D equation to get diameter formula in terms of A and B. So A and B are the stress values, right? Ultimately, okay? And that's the result. That's the handout that I give it to you guys for the shaft diameter calculation. And this is also already coded into an Excel, which I'll show you in the next lecture here. Okay, so you can save yourself a lot of time and confidently using a template for shaft design. So back to so this is a summary here. Okay, summary here. For under different loading conditions, some loading conditions really simple. The most general one is this. Okay, so this is most for your design project. This is probably the formula that you're going to choose one of them. Either one of them is fine. I think I don't remember if I probably specify good in my lines here for the projects. Okay, yeah. Okay, so this slide here basically shows if TA is 0, mm is 0, and how that equation basically be simplified further, right, to become this one here. Okay, yeah. Okay, so basically the formula, it's not really anything new because this is design. So the formula here is in terms of the calculation for the diameter. It's not just the calculation for the safety factor anymore. Right? Previously, we often focuses on calculate safety factor. Let's see if the safe or not. Okay, that's most of the focus. But in this part, you need to basically come up with the shaft diameter. And how do we do that? Those formulas will serve as the basic calculations. Okay, for you to come with the shaft diameter. Okay. So I'm going to continue here next lecture, and I have an example to present it to you. Okay. Any questions? Okay, yeah.